Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Extremely happy to have Yaron Singer here from Harvard, and he's going to talk to us about some limitations and possibility towards data-driven optimization. Thank you.
All right, so thanks, Yael, and thanks everyone for coming. I've seen many of you in Portland, so thanks for coming all the way from Portland down here so that we can meet. Right, so every time that I come here, like half of the times is to give a talk. So, and I regret like not coming more often. So, thanks. Yeah, all right. So thanks for not making me feel too guilty about that. All right. So let me just start off with this is I know I don't know what the format is, but let's make this as informal as possible, and you guys should ask questions at any given point until I tell you not to. Okay, so but let's keep that protocol. All right, so Madhu, all right, okay, all right, so I'm going to start with this like trivial example of figuring out how to get here from my office. Okay, if you make the mistake of driving, oh, this is a Google Map, sorry, so this is a Bing one. Right. But for the purpose of this example, I'm going to stick with this one, right? So, so I'm trying to route from I'm trying to route from my office here right down to down here, right? And somehow the Bing algorithm knows how to knows how to find a path that's gonna take me there in reasonable time. So if we try to kind of look into the procedure that happens there, right? Then there are two components of that, right? So and I mean there are many components of that, but I'm going to treat them as two, okay? And one part is going to be the machine learning part, and the other part is going to be the algorithms part. And what I'm going to talk about is I'm going to talk about the intersection between these two things, okay? So the machine learning part is the part that learns the model, okay? So it thinks about this problem as a graph, right? It puts nodes at junctions. It then puts edges right between these nodes, and then using various data sources, it figures out latencies on these edges, right? And these latencies try to model how long it's going to take, getting from one node to another. Okay, and then once we have a model, then comes the algorithm part, right? And the algorithm just takes that graph, it ignores everything that happened before, and it finds this finds the shortest path according to this model. Okay, and we do this all the time. It seems like pretty straightforward. The kind of from a machine learning perspective, these things are easy. From an algorithms perspective, these things are easy. You learn the shortest path algorithm in your in undergrad, right? So these things are very well understood. And right, so what happened here is we went from almost without noticing, right? We started from data, right? We had some sort of machine learning application, that took these data sources to designing this model, right? And then the algorithm took this model as something that's as a given, and then made a decision. And the decision here is the path, right? So you can ask, what happens if this machine learning algorithm is wrong? Whether it's wrong because it can't be right? Whether somebody, maybe there's like, I don't know, some bug, or if you want, there's like just too much data, right, to find the true latencies. Okay. Some of the edges are missing in here. Yeah. Well. Yeah, so right, so it's not a complete graph. It doesn't have to be. If you want, it can be, but just for some of the latencies. Right, so this is just me not doing my job well. Right, but don't worry about that. Okay, I mean that's going to happen so many more times in this talk that you'll wish it was that. Okay, so okay. Right. So so now, right, we can ask what happens if these, if the latencies that that are here, if they're computed, if there's some sort of estimation error, how is that going to affect the decision? Well, it's like a trivial exercise to see that it's not gonna have any effect, or or it's going to have this very minor effect on the outcome, right? And what I mean by that is, so suppose that instead of the true latency, you're 1 plus epsilon, right, from away from, your estimation is 1 plus epsilon away from the true latency, right? And then run the shortest path algorithm. You're going to have an answer that's roughly 1 plus epsilon from the original shortest path. Okay, so it may change your decision. Okay, you may take a different path. Okay, I'm not saying you're not going to take a different path, but if you take a different path, then fine. The total latency of this different path that you may be taking is going to be at most 1 plus epsilon, 1 less epsilon from the truth. Okay, so no major dramas here. Okay, so let me just do another quick example. This is an example of influence maximization. So what it is basically you have a social network, you have nodes in the social network, and you want to select a few people who will spread information in the best way possible. Okay. So this is my idea of a social network. Again, we're going to build a model. I selected some nodes here in blue. Maybe that's not so visible, but now I'm going to add edges. Maybe that's a bit more visible. Okay. In the same way, we're constructing a graph. Here, instead of latencies, we're going to have probabilities. Okay, these probabilities are going to be a probability that one person forwards information to another person, given that they received information. Okay. And now we're constructing this model. Then an algorithm is going to come. It's going to select nodes to spread information, and then that's going to have an effect. And then the effect is, okay, we lost that slide. The effect is the number of nodes that are influenced. Okay. So again, we went from data. Here the data was the social network. It's probably some other observations of these influence processes so that we can infer these probabilities of, of who infects whom and, by how much, right? There's this machine learning algorithm. It's a black box, created this model, and then that model, then an algorithm comes, takes that model, and makes a decision. Here the decision is which nodes we're going to select to be the influencers, okay? So the difference between these two examples is that in the influence maximization example, small estimation errors can be critical. Okay, they can seriously affect the outcome of the algorithm. Okay, and let me just give you this really sort of pathological example. Okay, so let's say that we just have a line graph. Okay, and we're going to select this node, and we want to infect or have as many people as we can receiving information, right? And on these edges, what we're encoding is we're encoding the probabilities of one node forwarding information to another node. Okay. Let's say that in reality, the truth is that they all in fact they all pass information with probability 1. Okay. And now we look at the expected number of nodes influenced by this model. It's going to be n. All right, the number of nodes in this line. Okay. But now if we have if we look at an estimated model, and we can just say, so suppose that now that I estimated every edge, instead of being 1, it's going to be 1 minus epsilon, right? And now I look at the expected number of nodes that are going to be influenced, or the expected number of nodes that are going to receive information when one node sends the information, then that's going to be just a constant. Okay? So the ratio between the number of nodes that are actually influenced and the number of nodes that are estimated to be influenced goes to infinity as n goes to infinity. Okay? So, and what that does is you can cook up now examples, as many examples as you like, right, where the algorithm actually makes a very wrong decision. Okay? And like when we quantify this, right, there's no real difference, right? Like, we have two problems that are solvable, if we know how to optimize them, right? Or, if we know the model that we're optimizing over, right? And here in the shortest path problem we have an epsilon error, and here we have an epsilon error, but the consequences are drastically different, right? So we want to sort of have some sort of formal understanding of when this happens, does it always happen, right? and what we can do about these things. Okay. So there are actually a lot of questions that you could be asking in this space, but I'm going to focus on two main questions. Okay. And the first question that I'm going to focus on is this question of robustness. So what I'm going to be asking is, so given that we have some sort of error, right, or noise in the model, okay, can we design algorithms, right, that make the right decisions, right? And I'm going to formalize this in just a couple of slides. Okay. The second question that I want to ask is about optimization from data. So, forget somebody giving me a model that's wrong. Okay. Suppose that I have observations and I want to make a decision. Okay. Is that in general possible? Okay. And I'll formalize that towards the end of the talk. All right. So, Glenn, you had a question?
I was just going to say, so there's your example reminded me of a paper in economics called the O-ring theory of development, which is one where you have like many stages of production, and like every stage relies on the integrity of the previous stage and so forth. And that's known to lead to some very pathological sort of outcomes that don't happen when there's sort of like substitutable inputs at each stage. And I wonder if there's any formal connection between the structure of that type of a problem and what leads to these, robustness or not here. I'm not sure.
Right. So that's a great question. So first of all, I don't know that model at all. In general, right? But it sounds like this is the sort of thing where we have these sort of cascading effects, right? And these sort of things take place. And that's right. So I mean, I'd be really interested to see what happens there. I'm going to talk about things that are like one level more general than that, so that we can kind of have a more formal discussion. But I'd be glad to to take a look at that.
So I'm not completely sure I see the difference. So going back to the map example.
Sure. Yeah.
And suppose that in each edge, let's say in reality it's 1. But it becomes 1 minus epsilon.
Yes.
So it's very small, it's epsilon. But now if each edge you take now adds an epsilon, then you add epsilon times n. To your driving. So
right.
There's also a cascade of, also there it can be a terrible.
No, that's right. But when we look at the ratio between, right, but if you just look at there's like the.
This is epsilon n.
The ratio. Okay, so you look at the multiplicative ratio as opposed to the difference.
Yeah, I mean, but this is just for, I'll talk about additive ratios actually in a couple of minutes, and I'll just say a sentence and I'll remind you about that. But that's a great question. Okay, so all right, so I want to start with talking about how do we do optimization when we have error and noise. So this is when we have error and noise in the model, and this is joint work with Avinatan Chassidim. He's at Bar-Ilan University and also at Google. Okay.
Is that really the title?
I wanted to do that for the paper and I didn't have the guts. Like how pathetic is that? So I'm just doing that for the like in the talk, right? So here's the thing. Okay, so let me say this better. There's one paper we submitted to Theory Conference, and then that had a different title. But then like then there's like a paper for Machine Learning Conference, and that like demanded like using something like that. But then you don't want to mess with them, right? So anyway, no. All right, so so I'm going to take it up a notch just a little bit. And I'm going to, again, start with an example. So I know we've seen 2 examples, but this one is going to sort of convey kind of the main idea of what's going on here. So I'm looking at this problem called Max-cover, and this is sort of this kind of very basic problem in computer science. And the goal in this problem is you're given a bunch of sets, and these sets cover elements of some universe, and you want to select k sets so that you're maximizing the number of elements in the universe that you're covering. Okay. And what I'm giving you here is I just cooked up this like extremely sort of simple example, right, where we have 2 elements in the universe. They are covered by a bunch of overlapping sets, right, and then there's a series of elements that are each covered by a set, and it's covered uniquely by a set, right. And now if I asked you to solve this problem, right, to give me a simple algorithm, right, that gives you a good result, right, then does anybody have an idea of what you would do for this instance?
First,
One from the first and a minus one of the others.
Okay, thanks, Nicole. Thanks, Madhu. You can joint author the paper. Exactly. Okay. So right. So this is like like this ridiculously simple instance, right? What we're going to do is we'll just select like one set from here, and then just keep on selecting elements from the remaining ones until until we run out of budget, essentially, right? And that's going to be optimal. Okay. But now, suppose that, let me just say, when I say optimal, I'm going to talk about approximations. So from now on, I'm going to say that an algorithm is an alpha approximation if the ratio between the value that's returned by the algorithm and the value returned by the optimal solution is at least alpha. Okay. So in general, what we want is this alpha to be as large as we can. We want it to be 1. Okay. And we're going to be happy when this alpha is a constant and does not depend on the size of the problem, right? So a solution of like a half here, as computer scientists, we're happy with. But like if it's like 1 over log n, we're going to be not so happy with, because as n goes grows large, then then the solution becomes worse and worse. Okay, so the goal is to get like these alphas to be constant, right? I'm sorry?
like you need this like bound from another side.
Also, there's the value. You need to ask what's the definition of the value. It's the number of points we cover, I assume.
Yeah, here's number of points. It's just the number of points that we cover, right? Okay, so now suppose I'm going to give you exactly the same example, but now I'm going to tell you that that instead of actually seeing the data, right, and in this case, the data is this, right? So I'm going to give you an oracle that's going to tell you the value of every set, okay? But the crux is that this oracle is going to have a slight error, okay? So what is this error that this oracle has, okay? So on pretty much everything else, it behaves like you want it to. So when you give it a subset of sets, right, it returns the actual value of them. It returns the number of elements that they actually cover, okay? Except if you ask it to the value of one set from from this group, right, and one set from this group, it's going to return the number 2. Okay, so it's a very small and local error. Okay.
It should have been 3. Giving it
Exactly. It should have been 3, right? Because the union of this set and this set is 3. Okay, but this oracle is wrong, so it says that in this case it's 2. Okay. So if you now try to mimic the Nicole and Madhu Singer et al. Algorithm, right? What's gonna happen with this oracle?
So you don't see a reason to pick one element of B.
Exactly, right? So this algorithm is going to go ahead and it's going to select one of these sets, right? Takes it, and then as it tries to, and then it goes and says, well, should I take something else? And then it looks at every one of these sets and it says, well, no, because it doesn't add any value. The value stays at 2. I'm done. Okay, so it returns value 2 when it really should have returned value k plus 1. Okay, k can be as large as n, right? So this is very bad, right? So this algorithm is actually So it turns out that I forgot to tell you that this algorithm is not Nicole and Madhu's algorithm in mind. It's actually a famous algorithm called the greedy algorithm. Okay, and this greedy algorithm is sort of it's something that we use a lot. I'll talk about that in a second. So this greedy algorithm actually fails. Instead of giving us the optimal solution once we have a small error, right? Then the solution the value of the solution becomes very bad. It becomes 1 over n. Okay. All right. So let me pause on errors for a second, and let me just jump into talking a little bit about submodular functions. I'll talk about the greedy algorithm, and then I'll get back to talking about errors and how they relate to this. Okay, so this Max-cover problem that we just saw, this is an example of the submodular optimization problem. So what does it mean? It means that we have we're thinking about this in a more abstract way. There's a function that we're trying to optimize. It's a function that it's a set function. It takes subsets of elements and returns reals. Okay, and we're going to say that a function is submodular if the union if you take any two sets and you look at the union of them, then the value of the function is going to be smaller than their sum minus their intersection. Okay, so in Max-cover, if we take two sets, right, then this is their union, right? The value of the union of two sets is 3, right? Which equals 2 minus 1, right? This is the value of every set minus the intersection. Okay, so Max-cover is an example of a submodular maximization problem. And we say that this is a submodular maximization under a cardinality constraint, right? Because the cardinality here is k. We're maximizing this function so that we're selecting no more than k sets, right? Otherwise, it would be trivial, right? We would just select all the sets. Okay. So an equivalent definition is this one that says that a function is submodular if and only if it has this diminishing returns property. Okay, so what does this say? This says that when I'm adding this element A into S, I'm looking at the marginal contribution of this element. I'm looking at f of S union A minus f of S. This is the marginal contribution. So if S is a subset of T, right? So as S grows into T, right, then the marginal contribution of adding A diminishes. Okay, it just goes down. This is what we call diminishing returns property. Okay, so these two definitions are equivalent. You can think about this in in any way that makes more sense to you. And the nice thing about submodularity is that it has so many nice desirable approximation guarantees. And I'll say later, this is arguably the most general class of combinatorial functions that we know how to optimize. Okay, I'll be more specific about those things later. So why do we care about submodularity so much? It turns out that many canonical problems that you know from theoretical computer science can actually be stated as submodular maximization problems or submodular optimization problems. Max-cover, min-cut, knapsack, maximal matching, spanning trees, just a bunch of them. In game theory and mechanism design, we heavily use submodularity because it gives us a reasonable model for modeling agents' valuations for subsets of items. So if you're an economist, you've probably seen or thought about gross substitutes. And submodularity is a superclass of that. Okay? So these are, so gross substitutes are these valuation classes that guarantee you these nice equilibrium properties. So they're sort of basic notions. And finally, just in machine learning, there's been kind of an explosion in the application of submodularity. So apparently, functions like the entropy, mutual information, cut functions that are used for vision applications, clustering, influence networks like the one that we saw, all of them are submodular functions. Okay, so there is just a huge trend in machine learning in using this submodular optimization. All right, so going back to this, as we get closer and closer to thinking about errors, so this other thing about submodular functions is that in general, these things can be exponentially large. So we need, when we're thinking about them as being represented through a value oracle. What's a value oracle? Basically, I give the oracle a set. It returns to me the value of the set. That's it. Okay? And as I said before, so it's arguably the most general class of functions that we can think how to optimize. If you think of a slight generalization of that, then a result by Mirochny, Shapira, and Vondrak in 2008 shows that there's some information theoretic impossibility. Okay? So the question that we want to ask is, now that I've hopefully convinced you that submodular functions are the most general and great and wonderful thing that you could hope for, right? And if I haven't, then talk to me after the talk. Then what we want to understand is we want to understand whether these nice approximation guarantees that we already have for these functions are maintained once we have these small errors. Yeah? Go ahead.
So what if you have something that's like overall submodular but has little supermodular clusters inside of it? So like rather than, imagine you've got some big instance of a problem and like the submodularity of it is growing in it, but the supermodular components are either like of constant size or growing much slower than the submodular components are in some sense. Then does that mess up the subproducts?
Well, I mean, so the thing is, right, so at this point we don't know, right? So what we need is we want to have, right, so you're asking, suppose the function is almost submodular, right? I mean, and then, right. So I'm going to give you a definition. So I'm going to give you a definition, you tell me if you're happy with it. Okay, so following up on Glenn's question, I prepared the slide. Right. So what I'm going to ask is, so let's formalize this discussion. Let's say that if so let's say that we have a function that's submodular. We don't have the real oracle. We have what we have this what I'm going to call an epsilon error oracle. Okay. And what is this oracle? For every set that I query this oracle, right? This oracle is going to return to me an answer that's guaranteed to be between 1 minus epsilon and 1 plus epsilon of the true function value. Okay. So this is along the lines of what Glenn was asking, right? So it's not exactly locally submodular, but it's always right, like very close to one true submodular function, right? So now, right, in the Max-cover example that we cooked up before, right, then it was actually a 1/3 error oracle, okay? And you can actually trick the greedy algorithm with any epsilon. So instead of putting 2 elements here, you put 1 over epsilon elements, and you have the same example. Okay. But the fact that the greedy algorithm fails doesn't mean that any algorithm fails, right? So what we want to ask is, are there desirable approximation guarantees for optimization when we have these small epsilon errors? And the answer is no. Okay. So in general, there are very, very simple monotone submodular functions. Monotonicity here just says that as you're adding more and more elements, the function grows. There are very simple examples of these monotone submodular functions, right? Such that if I only have access to this epsilon error oracle, okay, I'm not going to be able to get any reasonable approximation in less than exponential time, in less than exponential number of queries to that oracle. And what's a reasonable approximation? This is roughly square root of n. Okay.
So the Max-cover example is a coverage function.
Yes.
Is this example also a coverage function?
No.
Okay, so in principle you could.
Yeah, that's a great question. So the question is like in these examples, right, that I gave, right, like so I use this Max-cover example, and the question is, whether what is this? What are these simple monotone submodular functions, right, that make this fail? So the answer is it's not a cover function, If I showed you these functions, you'd be horrified. These are almost linear. These are almost additive functions. These are affine functions.
Really?
Yeah.
You mean linear functions?
Affine plus.
Okay, or constant. Okay.
Yeah.
And there's some constraint, like you're maximizing subject to a constraint.
Right. Exactly. Right. So what's the optimization problem? The optimization problem is to maximize. It's like in the Max-cover, you're maximizing a monotone submodular function under a cardinality constraint. Exactly.
And the constraint is not like super crazy.
And the what? Sorry.
The constraint is not super crazy.
No, the constraint is cardinality constraint. You're allowed to select most k elements.
So if you want n to the 1/2 plus delta, then it's fine.
If you want what? Sorry.
You're allowed to have slightly higher than square root error, then you can.
Yes. So actually, that's another. It's actually tight. There's an algorithm. You can actually. It's not the greedy algorithm. There's a different algorithm. It can give you square root of n. I mean, but square root of n is almost like at the border of like our worst nightmare. You know. I mean, when we're thinking about these things, it's like, if it's 1 over n, then, you haven't done anything. If it's, also, and if it's square root of n, then, then it's, right? You wake up screaming in the middle of the night, right? So, okay, what does this mean, right? It means that these sort of general frameworks that we have for optimization, they're hopeless unless, we have, like, exactly the function value. Okay? So I'm gonna defer these like the conclusions that I have from this to the end of the talk, and I'll be glad to talk about these things offline later. But this is so I've been walking around with this result for a while. I actually presented it here more than a year ago. Like, this is an impossibility result. If you guys, hopefully you don't remember. Yeah, it was kind of like this weird thing where Omer convinced me to give a talk about something that I haven't proved yet, and I thought that was a great idea. And then, like, on the day, I realized I'm not gonna, it's wrong. Like, I'm trying to prove it's wrong, so I had to give another talk. So I gave this. I gave this talk about the lower bound instead. So yeah, so it's kind of depressing, and to me it was, so where's the hope? Where's the light, right? Because otherwise I felt like, Harvard should fire me. I've been doing some modular optimization for a while, and if I told people that, if you have like a small error in your in the evaluation of your function, then none of the things that you've done are useful, and since so many of my things have been applied, then I felt that that's.
But this only applies to worst case model of error that you described.
Okay, so hold on to that thought for like 30 seconds, and before I dive into that, let me just give you a remark. This like worst results apply for convex optimization. Okay, so in giving this talk, so so machine learning people are always happy to hear about this result because you idiots working with this sort of submodularity and these sort of these multiplicative bounds that make no sense, right? This relates to the L's question. So no, this also, worst results hold for convex optimization. You have like these extremely simple convex functions. Even if you talk about additive approximation ratios, it goes to hell. Okay, so this, I'm sorry.
What assumptions on the convex functions?
It's convex. I haven't checked. Well, it can even be smooth. It can even be it can even be strongly convex. So even for strongly convex, this is going to hold.
Do you have exponential to get?
You need exponential communication to get. You can do this for multiplicative, and you can do this for additive as well. We can chat about this later, but that's exactly my point. Like, this is bad. I'm not making any recommendations. I'm telling like my personal feeling about this, and you all can have Okay, so in attempts to save my job, so I was thinking, what's the right? Where's the positive? Just like taking a step back, right? So what we're doing is we're looking at we're going from data, right? There's machine learning, and we're in this part, right? We got this wrong model, right? And we're trying to make the right decision. So let's look at an equivalent definition of error. Okay.
Isn't a submodular model, is it this best one?
This one, it actually is. It actually is, but we can talk about that later. Okay? But you're absolutely right that.
It's less submodular about the way in which the errors are interacting in that model.
Well, I mean, so you're absolutely right that there is actually more structure in that model, and then the impossibility result does not say anything about this influence example that I gave, they're actually positive results for influence. But I can tell you about that a bit later. Okay. Okay. So here's an equivalent definition of error. Okay. So an equivalent definition of error is just going to say, well, I have this oracle, and this oracle returns to me this psi of s times f of s. Okay. And this psi of s just happens to be between 1 minus epsilon and 1 plus epsilon. All right. So I'm going to relax. So and as this question was like this, this is small, but it's worst case. So what I'm going to do is I'm just going to relax that and just say, what, it's not worst case. It's drawn from a distribution. And what I'm going to do is I'm going to replace this constraint that is between 1 minus epsilon. You want me to lift this up? I'm going to replace this. I'm going to replace this constraint that this error is between 1 minus epsilon and 1 plus epsilon to this constraint that is just drawn IID from a distribution. But I'm going to assume very little about that distribution. It doesn't have to be. It's not going to be bounded on the 1 minus epsilon, 1 plus epsilon. It can be very general. Okay. Obviously, if this distribution is the identity 0, there's nothing I can do, right? So we have this sort of very safe definition of distributions that we're going to be able to work with. Okay. So now the question is, this is error, this is noise, right? We know that we can't do anything for error. Can we do anything for noise? And right, so are there, again, desirable approximation guarantees for noise? And for noise, the answer is positive. There's a constant factor approximation for maximizing monotone submodular functions under matrix constraints. And if you're in this business, then you know that this is like one of the sort of most sort of general things you can hope for. It's not tight yet. Maybe it will be. Some things are tight, and I'll talk a little bit about that. Okay, but the point is that once it's noise and not error, then all these great things can come up. Yeah.
So now you're measuring performance by expectation, taking respect to these.
Right. Great question. So you can also look at high probability results and okay.
This matrix constraint is now replacing what used to be just k people.
Yeah. It's more general, right? So okay. So let me just say a few things. So in this talk, I'm just going to stick to the uniform matroids, maximizing f of s such that the size set is at most k. And the result, like this result, is actually made of two separate results, two separate algorithms. One works for what we call large k, so this is k when it's larger than O of log n, and the other one is k when it's smaller than O of log n. So what I'm going to do is I'm going to spend 5 minutes talking about this result. I'm going to wave my hands, giving you like some flavor of what goes into showing this, okay? And then I'll spend 5 more minutes about I'll take 20 steps back to the beginning of the talk where we had this other question, where we're talking about optimization directly from data, and I'll spend 5 minutes about that, okay?
Are you going to say anything else about the distribution? Your assumption on the distribution?
These are I'll give you the formal definitions, but they're very, very all the distributions that fit under this definition. We call these almost bounded distributions. It's just it's just we're just making sure that it's not constant. We're just making sure that that there's just enough information that we can work with. It's
the same distribution on every set.
It's the same. It's exactly. Yeah. If there is ID, same distribution. If it's not the same distribution, if it's correlated, we can show I can show you a lower bound in 20 seconds. Okay.
So same distribution for the
You have you can cook up the simplest examples that will fail you with that. Okay. So in some sense, it's the right model. Okay.
Just curious. You have a very general result up there.
Yes.
You're saying I'm only going to talk about a very special case, but even that special case is breaking up into 2 parts. So.
Well, what can I do?
Are you going to say anything about what you do to get
the matrix constraints?
Yeah. Is that a completely different theorem?
No. Oh, okay. Great question. Okay. So the matrix constraints are basically are a variant of this algorithm. This algorithm is almost tight. This one isn't. We're desperately working on a whole new framework for getting this for changing this algorithm.
Would be the rank of the matrix?
Well, it's here like when you go to the matrix constraints, like you don't have this. You no longer have this this large K, small k. You're just going to apply a variant of this algorithm, and it's going to give you like this horrible constant, but it's a constant. Okay, so that's that's our business. All right. Okay, so 5 minutes on this. Okay. Okay. So so now let's formalize this greedy algorithm. This greedy algorithm this is the reason why people get into submodular optimization, because it's like the simplest thing that you can do. You run this like trivial algorithm, and you get like this great result, and you're happy, right? So this is a great selling point for this area. So all this greedy algorithm does is it just like starts with the empty set, and then at every until it has k elements, it's just going to select the element that has the largest bang for the buck, right? So it adds to S the element A that's the argmax of this. Okay, that's simple. So this greedy algorithm, it's actually known to be the optimal approximation ratio. So this greedy algorithm was actually analyzed by Nemhauser, Walsley, and Fisher in 78. Okay, it's shown that it's 1 minus 1 over E. And then Uri Feige showed in this is the journal version in 1998, 1994. Like he showed that essentially you won't be able to do better than 1 minus 1 over E unless P equals NP. Okay, and this paper that I mentioned earlier, Mirakni, Shapira, Vondrak, different result in that paper shows that you can do better than 1 minus 1 over E unless you use exponentially many queries. Okay, so this is like a different model, but anyway. 1 minus 1 over E is what this algorithm gets you, and this is tight. Okay, so now if we look at this algorithm, right? So what are the things that we have to know how to do, right? And what are the things that we don't know how to do when we have noise, right? So we know what the empty set looks like, right? And we know to stop when when we haven't selected k elements yet, right? So the only thing that we don't know how to do is we just don't know how to like implement this line, right? So what does this line ask us to do, right? This line asks us to essentially at every step find the largest set. Okay, so this really reduces to, if I give you two sets A and B, right? Is the whose value is larger, right? And the crux is that now instead of having the true values of the function, of course you have the noisy versions of them. Okay, that's what we have to know how to do. So let me just say let me give you like the general technique of what we do, okay? And this is true for both algorithms, right? So before you look at this, just think about what you would do if you were doing this in continuous optimization. If you had continuous optimization and you had noise, right? Here's what I bet you guys would do if you thought about it for 20 seconds. You'd say, okay, I want to. You have 2 points and you want to know which one has the larger value, okay? You know that, and now you know they have noisy evaluations of them, okay? So what you're going to do is you're going to select like this small epsilon ball around these 2 points, okay? You'll average it, and then you'll ask, okay, now which one is larger, right? And from concentration bounds, you'll know that you're right with high probability. So what we want to do is we want to mimic that into this world of combinatorial optimization.
So you're still following the greedy algorithm, but you're doing
exactly. So all I need to do is I need to replace this one line here of the greedy algorithm with this box, okay? And that's all I'm going to do, okay? So how do we mimic this sort of averaging, okay? So what we're going to do is in general, we're going to take sets, H1 through HL. And then what we'll do is, what we want to know is we want to know whether A is larger than B. So we will compare A union H1 and B union H1, and we'll do that like L times. And then we'll take the set that won the majority of these comparisons, okay? So the thing that makes this non-trivial is the fact that once we're talking about this sort of combinatorial optimization, then we have these effects of these smoothing sets H, right? So let's say that I have two sets A and B. A is larger than B, has 2 elements. B has 1 element, right? Now, right, I'm going to add H, right? So now H union A is going to have exactly the same value as A, but now H1 and B, that has a larger value, right? So somehow, like, right, the fact that I'm dealing with sets that can overlap makes things difficult. Okay. So this is a sketch for the algorithm for large K, and that's the only thing I'll talk about. And this is just going to be 2 slides. Okay. So we're going to do the smoothing technique by the following thing. We're going to arbitrarily select a set H of size log n. Okay. And then we're going to take all the subsets of this H. Okay. And we're going to make these comparisons. So what I'm doing is I'm taking, like, I'm just arbitrarily selecting H elements, and I'm throwing them out, and I'm kind of going to like treat my instances as if these elements didn't exist. And the idea is that I'm taking only log n elements so that it's small enough so that it's not going to affect my solution too much. But at the same time, when I'm looking at all the subsets of these log n elements, then I can amplify that into getting polynomially many results so that I'm getting concentration. Okay. Yeah, Omar?
Maybe I understand, but I mean, if K is large, then K could be log n, maybe, and if you arbitrarily select H, can H just equal A?
So I mean, what I'm saying is, like, large K, like, think about 100 times log n.
K is 100 log n. Okay,
Yeah.
so H could be a subset of A.
H could be A.
Subset of A.
So no, I'm taking these elements, and then I'm taking them, like, I'm putting them aside, and then making, like, all my comparisons, right? As if.
Algorithm is not allowed to select from those.
Yeah, exactly. Like A and B are not. Okay. And now, how and why does this work? Okay. So here's my one-line proof. Okay. So this is the set H that I'm setting aside. Okay. And ideally, what I want to tell you is that you can put it aside and sort of use it for comparisons and forget about it. Okay? But it's a bit more intricate than that. Okay. So what's the guarantee that I can give you? The guarantee that I'm going to give you is I'm going to say the following thing. So think of these are the gray elements. Okay. This is the gray area. Okay. So what I'm going to tell you is that if I selected A and not B, so here B is larger than A. Okay. But if I selected A and not B, then what that means is that the gray plus white area of A is larger than the only white area of B. Okay? I know this should be like red and blue, but sorry. Okay? Okay. So this is the guarantee that I have. Like, if I selected A, right, then formally, right, this is what I just said, right? The value of selecting S union A is greater than the value of then the value of f sub h is f sub h means only whites. Okay, this is you're ignoring the gray. Sorry, guys. Yeah. Okay. Anyway, possibilities are endless now, but so other consequences, right? So, all right. So we did that, and then I can push this all the way to say that now f of s is going to be 1 minus 1 over e of opt sub h. Opt sub h is the optimal solution that ignores h. Okay, there's some analysis that goes on here. It doesn't matter. So here's what's happening. The optimal solution is less than the optimal solution sub h plus f of h. For this, I have 1 minus 1 over e approximation, and then this is h. So what I'm going to do is I'm going to push h back into my solution, right? It's size log n. I'm saying that k is larger than, is much larger than log n. So I can like push log n elements without it having, major consequences. This is not going to be exactly 1 minus 1 over e, but then you can do this something that we call the slick greedy algorithm. What it does is it just, to whatever precision that you like, it, checks a lot of options, does like a comparison between them. You analyze it, and that gives you, for large enough k, that gives you 1 minus 1 over e minus epsilon. Okay, that's it. That's the technical part. In general, for small k, you can actually show a lower bound. You can't do better than for k equals 1, you can't do better than a half. Okay, it's actually a much more challenging case. The algorithm it's a completely different algorithm. It uses this idea of smoothing sets, but it's the approximation guarantees are much worse. The analysis is kind of different and harder. But anyway, the result is that for any monotone modular function, once you have noise, you can get constant factor approximation guarantees for maximizing that function under a matrix constraint, even if you have like this noisy oracle. Okay, so that's that result. Okay, so I'm going to conclude with my -5 minutes with just talking about this optimization from samples, and I'll just say. I'll just do like 2 slides. And this is joint work with Thibaut Aurel and Jean-Pouget Abadi, who are both students at Harvard. So before, right, we had this model to decision, right, where we're given the model and we're making the decision. Now we're going to look at the whole picture. And what we're going to do is we're going to see whether we can skip the step of formulating a model and just going straight from these observations into making a decision. Okay? So what I'm going to say is, suppose that a model is learnable from observations. And if you knew the model, then you can optimize the decision efficiently. Right? So the question is, would we be able to design algorithms, right, under this, like in this scenario, right? Because otherwise it doesn't really make sense, right? Like it seems like if I gave you a model that's, that you can't learn from data, right? Then why would you expect to be able to then optimize something that that you can't even learn from data? Okay. And obviously, if you can't optimize it efficiently, then why would the problem become easier if you didn't know what you're optimizing? Okay, so kind of slightly more formal, right? What I'm going to say is that we see observations, okay? And these observations are basically random sets and their values, okay? And these all random sets are of the same size. And again, we have the same objective where we're maximizing f of s, and now I'm saying that it has to be exactly k. Okay. And I'm assuming that now Si is drawn IAD. This is a sample. This is a random observation. Assuming that it's packed learnable. I'll say one word about that in the next slide, and then I want to maximize this. And I'm assuming that this problem is an APX, that it can be optimized efficiently or approximated efficiently. Okay. And then I'm asking, what is the best approximation that we can hope for in this kind of setting? Okay. Just a word about packed learnability, right? So this is modeled by Valiant in 1984. It's basically this kind of certificate that we have for models that are learnable, right? And formally, what this is a function or a class of functions is packed learnable if we can observe not too many reasonable number of examples, right, or samples, right, and construct some sort of surrogate that's going to give us the solution that's good enough, that sort of with high probability, right, behaves like the true function would. Okay, and this is sort of a very this is a framework that we have for predictions. In recent years, this has been extended, right, to actually learning some modular functions. And what I'm asking is it reasonable to think about these questions? Is it reasonable to learn some modular functions, right, if we're maybe not able to optimize them? So the result that we have is a spoiler. Unfortunately, you can show, again, very simple classes of functions that are packed learnable. If you knew them, you'd be able to optimize them in polynomial time. But you can't get any reasonable approximation guarantee unless you observe exponentially many samples, right? So somehow, right, what this means is that the frameworks that we have for learnability are designed for predictions. They're not designed for making decisions. Okay, and when we want to take it up a notch, and in some cases we just can't, because there's not enough information in the model. So what this says is that we need to, if we want to do this sort of data-driven optimization, and we want to be able to optimize things from observations or from samples, then we need to think about things in a completely different way. Okay?
Learnable says that you're trying to figure out from seeing a few samples predict the value of the function at some other.
Exactly.
And this you can do, but you can't find the best set.
Exactly. So essentially, what happens is like, you know, these when you look at these things, you know, the fact that you know a learning algorithm, right, can build a scarecrow, right, that for all purposes, for prediction purposes looks like a human, right? But now you want to, you want this human to play basketball, or the scarecrow to play basketball, and you find out that it's a scarecrow, right? Like that's kind of, this is like the best analogy that I have so far. Give me a year, and maybe I'll come with something more sophisticated, right? But this is like, to me, this is like, oh, obviously this is a scarecrow.
One question though.
Let me pause that question. Let me just in the interest of time, let me just conclude, and then we'll take that question. So just to conclude, our goal is to design algorithms that take, that look at the data and make good decisions, right? If we have small errors, or that can have a dramatic negative effect on the outcome. If that error happens to be noise, that we're lucky, good algorithms are out there. However, they're not the algorithms that we have right now. So if you're using some modular optimization anywhere that that matters, take a look. All these things that we have about learning and sketching and mechanism design, right? They use some modular functions. We have to rethink about these things because now, right? So I personally have been obsessed with this idea of whether what happens to mechanism design, if you think about polynomial time. But now, somebody says, forget that, right? Even if agents were behaving, truthfully, right, and rationally, and whatever you want, if they just don't know exactly what their valuations are, there are no approximation guarantees that you can give, right? So, so it says something about the benchmarks and the models, right? So that's the issue, okay? Same goes for for learning, right? You open all these learning papers, they have all these great experiments, but somewhere they learn these objective functions from data. If there's an error, then all these guarantees are are questionable, right? And the last point is that we saw that if we want to overcome all these things, we want to go to optimization from data. Then in general, that's impossible. So so it's a war, and right and we have to fight. So all right, so that's it. Thanks.
Yes. So there is somewhat of a type mismatch there, right? Back learning, I assume you are thinking in terms of additive error, while approximation guarantees demand multiplicative error. So
right.
Maybe that's another issue that will sort of prevent.
No, I mean, right. I mean, yes. I mean, so there's this this extended notion of PMAC learnability,
Yeah,
and
that would probably be even that would you would get the same result you're saying.
yeah. I mean, if I show you these functions, you'll either laugh or cry depending on your religion, right? So
the same as what Balkan and Harvey construct as hard examples for learning.
no, these are very very simple examples, very simple functions that just.
Any other questions?